So just finishing up with 11E, which was started in a previous video. When you have these mixtures, essentially the goal was to find the overall redox reaction that would give the highest possible electromotive force. And the one involving that would involve iron 3+ being reduced and the titanium 3+ being oxidized. And the question asked what reaction would occur at electrode A. All right, so this is electrode A right here, so that's the one that would contain the iron 3+. So this would be reaction that would occur. All right. So 11F asks you to calculate what the overall cell potential would be. All right. Well, if this is the reduction reaction and this is the oxidation reaction, all we have to do is write down the cell potentials for those two. All right, so this should actually say E naught equals positive 0.77. So you take that voltage, you add it to this voltage, and you would get this overall voltage right here. And again, when you're giving the answer, make sure that you put a positive sign in that, all right, because they are kind of sticklers for making sure that signs are indicated in that. All right, 11G says in the diagram above, label with an arrow the direction of the electron flow and the direction in which the positive ions would flow in the salt bridge. All right, so again, we can note that in this equation, in this half cell right here, that's where the reduction is going to occur. So that's where electrons are being consumed. All right, so this process right here requires electrons. So the source of these electrons in that half cell are going to be coming from the wire. So the electrons have to be coming in this direction right here. All right, so one thing that you'll notice about that is that in this half cell, what's going to be happening in the solution is that iron 3+ is going to be being turned into iron 2+. So over time, the solution is going to be becoming more negative over time. All right, and it's not, that might seem a little odd at first. It's just that this is a +2 is more negative than a +3. All right, so because it's becoming a little bit more negative over here, we have to have some positive ions coming in through the salt bridge to balance that charge out. All right. And just in contrast, if you look at what's going on in this half cell right here, taking away the electron, just looking at everything that's happening, what would be happening in the solution? All right, you have the +3 becoming this +2 plus these two hydrogen ions. So there's an overall +4 charge on this side, but there's only a +3 charge on this side right here. So this solution would be becoming more positive over time, and that would mean that the negative ions in the salt bridge would be flowing this way. 11H, I'm not exactly sure what that is talking about, so obviously we're going to skip that problem. And so 12A. So 12A is a problem where they give an overall redox reaction. And they then go back and ask for you to figure out what the half reaction is involving one of the components. All right, so this is kind of a problem which requires you to work in reverse. All right, so we're starting off with the overall redox reaction. All right, and one thing about this that hopefully you notice is we've got this ion right here, that's permanganate, and we've got manganese ion right here. And when you have a problem like this and the one of the half reactions is unknown, what that probably indicates is that the other half reaction is known. All right, so let's try to figure out what that known half reaction is. All right, and it's going to involve these manganese ions. All right, so here's the half reaction in your data booklet that it refers to. All right, so we're going to use this right here in this particular problem. And so all I did was I took the half reaction from the data table, and I went ahead and just doubled it. All right, and I've written the result of that right here. And the reason that I've doubled that is that then allows these amounts right here to be the same. All right, notice there's 2 manganese and there's 2 of these permanganate ions here. All right, and so this is what I'm going to use as the reduction half reaction. All right, so what I have up here, I've written right here, I've shown the total reaction, and right above that I've shown the reduction half reaction. All right, so we know that the oxalic acid, so if this thing is being reduced, then the oxalic acid must be being oxidized. All right, so all we have to do is figure out what reaction needs to be added to this to give our final reaction. All right, because this is the final redox reaction that's given here. All right, we know we can figure out what that reduction half reaction is. So what is that oxidation half reaction that needs to be added to that? All right, so there's a couple things that we can figure out. All right, okay, first of all, if the reduction half reaction had 10 electrons as on the reactant side, that means that the oxidation half reaction needs to have 10 electrons on the product side. Okay, second of all, one thing that would be missing is the 5 molecules of oxalic acid, so I'm just going to put those on the reactant side. I've got these 10 molecules of carbon dioxide. I'm going to put those on the product side. And let's look and see if there's something that's missing. All right, well, if there's only 6 total H pluses here, and there's 16 H pluses here, well, how would we get that to happen? What do we need to have in this reaction? All right, we would need to have 10 H pluses over here. And so if we have 10 H pluses on the product side over here, essentially what that means is that you would cancel out 10 of these over here, giving you that sum of the 6 hydrogen pluses over here. All right, and one way to check that is just to count up everything and make sure everything is good. So if we have the oxalic acid, we would have each molecule of oxalic acid has got 2 hydrogens, and if we've got 5 of them, that's a total of 10 hydrogens. So that works out there. Let's work out the charge balance. This is overall neutral right here. The 10 H pluses plus the 10 electrons, that means that this side right here would also be neutral. So when these two things added together, we would get that final reaction. So this right here would be the half reaction. And if you wanted just to show the half reaction in its simplest form, you could take the one that actually occurs here and just break it down to its simplest coefficients, which would be this right here. All right. One thing I want to point out is that in the rubric it says allow equation times 5, which means if you had written the half reaction in this form right here, they would have found that acceptable. All right. So in 12B, what they do is they give you the standard electrode potential for the half reaction involving the ethane dioic acid, which is the half reactions that we calculated in the steps before, and they give that as this right here. And so if we go ahead and write that down, so again, that is the oxidation reaction. We can write down that cell potential right there. The other cell potential we could get from the data table. All right, so in the data booklet, you can find this equation right here, and this is its cell potential. And if you want to get the overall standard electrode potential for the equation, they say the equation on page 10, they're referring to the overall reaction. You would get that just by adding these two together, and you would get positive 1.02 volts. All right, so I would go and put a V after this to give the answer. So I have to issue a little bit of a correction on this problem. So after initially solving this problem, as I just did in the video, I checked the answer in the answer guide, and I found out that their answer was different from mine, and I just figured out why, and I just wanted to explain what the difference is. All right. So notice here they say that the standard electrode potential for that half equation involving ethane dioic acid is this right here. All right, and if we go up, if we look at the reaction involving the ethane dioic acid, this is what we have here. And so initially, when I wrote that down, that's what I put in. I put in that negative value there. All right. The detail that's missing here, and this is very important, is that this is a standard electrode potential. All right, so this means that this is the electrode potential measured against that standard hydrogen electrode. And remember, in those, when they report these values, the reaction that they always show, the values that they always show for those standard potentials are for the reactions if drawn as the reduction. All right, and so that's the important detail here. All right, so in order for this to be the standard electrode potential, it would have to be this reaction right here drawn in reverse. All right, so this as drawn right here is an oxidation. To draw it as the reduction, you'd have to turn it around, all right, which would give it that negative value. All right, and so in order to represent that reduction reaction as an oxidation, we would have to turn it around, which would mean to write it as we now have it here, which would then change that sign to a positive. All right, so then that would change this part right here and give you an overall cell potential of positive 2.00. All right, and again, there should be a volts after that. All right, 12C says to explain the sign of the calculated standard electrode potential. All right, and it is a positive. All right, and what that positive it means is just to say that the reaction would be spontaneous as drawn. All right, and since the standard electrode potential is positive, all right, that means that delta. So again, positive standard electrode potential means spontaneous process, and in terms of delta G, that means that delta G would be negative. All right, so those are the completion of the problems. Hopefully that helps out, and good luck on the quiz on Tuesday.